We arrive at our last lesson for this unit, okay? So here's a brief warm-up question that ties into today's lesson, going all the way back to 6.1. So if you're rusty on 6.1 or a bit shaky, you can use your notes for this to answer our warm-up question, okay? So if a gas is maintained at a constant pressure, what will happen to the volume of the gas as its temperature increases? Explain why this occurs from the perspective of gas molecules and kinetic theory. Alright, so let's go ahead and take a look at our response here. So recall that according to Charles' law, for a constant pressure, an increase in temperature will cause the gas molecules to move around more kinetic energy. As a result, the molecules will take up more space, resulting in the gas expanding into a larger volume. And remember that we have to have the volume be flexible in order to expand because that's what keeps the pressure constant. Otherwise, if our volume is fixed, our volume cannot expand, and thus the pressure will increase instead. So today we're looking at our last topic for unit 6.4, thermal expansion. Okay. So some announcements: we have Unit 6 Quiz 1 on Monday 125, and then we're going to have our Unit 6 test on Thursday 128 and Friday 129 for 5th period on Thursday and 4th and 6th period on Friday respectively. So what we're up to today: Charles' law, a recap of temperature and volume, okay? Temperature and the volume of a substance, water and thermal expansion, thermal shock, mathematically modeling thermal expansion, and classwork 6.4 for the remainder of class. So again, Charles' law with a brief recap, okay? Excuse me. All right, if we have a container that's able to expand, like this container right here, okay? An increase in temperature will cause the gas molecules to move around more kinetic energy. So as a result, the molecules will take up more space, resulting in the gas expanding into a larger volume, okay? And again, because our container is able to expand, the pressure doesn't increase. The pressure remains constant. It's the volume that increases, okay? So we see there's a direct relationship between temperature and volume. I don't know why I have pressure there. That should say temperature, not pressure. So temperature and the volume of a substance, okay? So an increase in temperature will also cause solids to expand. Adding heat will give more energy to molecules in a solid, meaning more motion. So each material expands at its own rate, known as the expansion coefficient alpha of the material. All right, a higher coefficient indicates more expansion for a certain change in temperature, whereas the lower coefficient indicates less expansion for a same change in temperature, okay? So if we look right here with these railroads right here, what's happened with the railroad in this picture is the railroad consists of these steel tracks right here. So if the steel tracks underwent too great a change in temperature, the railroad will expand, and if the railroad has nowhere to expand into, it's going to expand outward, causing these wobbly tracks right here. Actually, this may not be a right picture. I've also heard this was an earthquake that may have caused this. Either way, earthquake or thermal expansion, the same phenomena can occur either way. So here's a weird anomaly: water. Water does not like to play by our rules, okay? Water is the only known substance that condenses as temperature increases. There are probably other substances that are very obscure and very niche, but I'm not a chemist, so I wouldn't know anything about those substances, okay? So conversely, as water temperature decreases, the water will expand, okay? So you can see right here, if you ever have water in pipes, like if you're in Boston or Flagstaff, a town that gets really cold during the winter, the water will freeze and expand, and it can cause the pipes to burst. All right, so let's look at, I think, per share, okay? Pipes that carry hot steam or are exposed to extremely high temperatures are often designed with loops right here. Okay, as opposed to being just straight pipes. All right, so in the condition of thermal expansion, within the context of thermal expansion, why might this be necessary? All right, so if we take a look here, okay, if we have extremely high temperatures, all right, so if our pipes become heated to extremely high temperatures, the pipe is going to begin to expand, just like we saw the railroad on the slide, 2 slides prior. So if they're not provided with space for expansion, the pipe will expand inwards on itself, leading to possible cracks and leaks. So instead of having our pipes expand inward on itself with a straight pipe, the pipe can expand inward without cracking because it has the space that right here it can expand into. And same thing right here is that the pipe at the top can expand outward. So it's kind of like you're pinching the pipe and allowing the pipe space to be pinched, but when it undergoes thermal expansion. All right, so we're, again, in more layman's terms, we're giving some flexibility to our pipe to expand into. Oh, man, I'm all over the place today with the pronunciations. I'm feeling a little bit sick with allergies today. So thermal shock, okay? Thermal shock is when the rate of expansion/contraction is too fast for material structure to handle, leading to a breakdown in the structure, okay? So if you've ever heated pottery too fast, you'll notice that the pottery can shatter. Or if you've ever seen Terminator 2, the classic James Cameron movie, T2 Judgment Day, as we're about to see, if you cause an object to freeze or undergo a drastic change in temperature too quickly, the structural material can be compromised and the material will shatter, okay? So this occurs if the expansion/contraction of an object occurs too rapidly. Rapid extreme temperature change, high expansion coefficient, low conductivity, cannot dissipate heat quickly enough. So these are 3 factors that will affect thermal shock, okay? Rapid extreme temperature change, aka your temperature change occurs too quickly. High expansion coefficient, okay? So let's say you don't have a extreme change in temperature, but let's say your material has a high expansion coefficient. Then that means for even a small change in temperature, your object's going to undergo an extreme expansion for a small increase in temperature, okay? And then low conductivity, okay? So let's say you have an object that is being frozen, okay? If that object has a low conductivity, okay, it's not going to be able to dissipate heat quickly enough, all right? So as a result, you have this problem of it's trying to be frozen, it's trying to give off heat, but it cannot do that. So as a result, because the low conductivity can't dissipate that heat quickly enough, it's going to shatter. Its materials or its structure is going to be compromised, okay? So let's take a look here at thermal shock then. Thermal shock with the classic Terminator 2 Judgment Day scene.
Writing's not that easy, but Grammarly
Once
can
we
help.
get through this advertisement
This
brought to you by
sentence is
Grammarly.
grammatically correct, but
Also, I would like to note that yes, this movie is rated R, but this is a robot right here, so there's no actual violence being shown, and there are no curse words in this scene. So our robot here has been exposed to liquid hydrogen or liquid nitrogen, one of the two, and so as a result, as liquid nitrogen turns into a gas, all right, that is going to take heat from our person here to cause that phase change. And so as a result, the robot, let me pause here to explain better for a moment. So because our liquid nitrogen is turning to a gas, that means it is absorbing heat, and that heat is coming from the robot. So as a result, there's a drastic change in temperature for our robot that compromises the structure of the robot.
Hasta la vista, baby.
So there is your thermal expansion in an actual Hollywood movie. All right, so let's look at how to model thermal expansion then. Okay, so let's say we have a rod of length L. all right, that's going to undergo thermal expansion. Let's say we add heat to it, causing it to undergo a change in temperature. Its temperature increases, and let's say it expands by a amount delta L. The equation that models this is given as delta L divided by L naught equals alpha times delta T, okay? So delta L right here is our change in length, okay? L naught is the original length of our object, okay? Alpha is the expansion coefficient, okay? It quantifies how much we expand, how much our object expands for a given increase in temperature. Or likewise, how much our object will compress for a decrease in temperature, okay? And then delta T we recognize as the change in temperature, okay? So let's look at some example problems then, all right? Example 1, thermal expansion problems. An aluminum rod has a length of exactly 1 meter at 30 degrees Celsius. How much longer is it when placed in a 400 degrees Celsius oven? Okay? So we start with our knowns and unknowns here for this example. All right? We recognize that L naught is 1 meter. That's how long we originally are. Our delta T, our change in temperature, is 370 degrees Celsius. Okay? Our alpha, our expansion coefficient, is 25 times 10 to the negative 6 per degree Celsius. It's not given to you in the problem. You'll be given the expansion coefficient in problems, or at least a sheet with expansion coefficients. So the expansion coefficient of aluminum is 25 times 10 to the negative 6 per degrees Celsius. Okay? I believe I forgot to cover this, but the units for expansion coefficient are per degree Celsius, just 1 over degrees Celsius. Okay? And then our unknown is our delta L. Okay? So we need to find what our change in length is. It's asking us how much longer is it when placed in a 400 degrees Celsius oven. So we're asking for a change in length here. We're asking for delta L. So we plug the information into our equation. So we have delta L over L naught equals alpha times delta T. So that gives us delta L over 1 equals 25 times 10 to the negative 6 times 370. We don't need to get rid of the 1 here because 1 is, well, anything divided by 1 is just itself. So all we have to do is multiply 25 times 10 to the negative 6 times 370, and that gives us that our change in length is going to be 0.00925 meters. So there's not an extreme change in length here. It's a very small change in length, which is what we would expect. We don't see drastic changes in length in reality, but we see small changes in length that we do have to account for, which you will explain, which you will delve into to explain certain features in civil engineering on your problem sets. Okay? So this is our first example here. So now let's move on to another example. Okay? So a concrete railroad tie has a length 2.45 meters on a hot, sunny 35 degrees Celsius day. All right, what is the length of the railroad tie in the winter when the temperature dips to negative 25 degrees Celsius? So notice here, okay, that the problem doesn't ask us to find the change in length, it asks us to find the final length, okay? So we need to find delta L, but delta L is not going to be the end of the story because we're going to use delta L to calculate better said, our final length, okay? So L naught, our initial length is 2.45 meters. Delta T is negative 60 degrees Celsius, okay? Because our temperature is changing from 35 degrees Celsius to negative 25 degrees Celsius. So delta T is negative here since our temperature is decreasing, okay? And then the expansion coefficient for concrete is 12 times 10 to the negative 6 per degree Celsius, okay? And then again, delta L is our unknown, but it's not going to be the end of the problem once we find delta L, okay? So again, we plug our knowns into our unknowns, we plug our knowns and unknowns into our equation. So again, we're looking for delta L. L naught is 2.45 meters, and then alpha is going to be 12 times 10 to the negative 6, and delta T is negative 60. All right, so as a result, to solve this equation, we multiply both sides by 2.45 meters, and that gives us delta L equals 2.45 times 12 times 10 to the negative 6 times negative 60. So as a result, we're going to get delta L equals negative 0.0018 meters. Okay? So we found delta L, but we still need to find our final length. So that's where we make use of a little fact from algebra, which is that the final amount of something is equal to initial amount plus the change in that something. Okay? So As a result, our final length is going to be given by our initial length plus our change in length, which is going to be 2.45 meters minus 0.0018 meters. So as a result, we get that our final length is 2.4482 meters. And we can see that this will make sense because we're undergoing a decrease in temperature, so our railroad ties should undergo a compression instead of expansion. So we should expect that our final length should be less than our original length, by an oh so very small amount, but an amount that can play a huge role, as you will see on your problem sets. So now let's go through a check for understanding problem here. All right. So take a moment to go through this check for understanding problem here, and then we'll bring it back together to go over. All right, so let's go over our check for understanding problem here. So it says a metal rod that is 0.5 meters in length is heated from 15 degrees Celsius to 95 degrees Celsius. The length of the rod increases by 9.6 times 10 negative 4 meters. We ask, what is the coefficient of expansion for the rod? All right, so L naught is 0.5 meters. Delta L is 9.6 times 10 negative 4 meters. All right, so that gives us our change. So increase indicates a change, decrease indicates a change as well. So our increase is 9.6 times 10 negative 4 meters. If we had a decrease, we would write this down as delta L equals negative 9.6 times 10 negative 4 meters, indicating a decrease. And lastly, our delta T, our change in temperature, is 8 degrees Celsius. We increase from 15 degrees to 95 degrees Celsius. Okay? And then lastly, our unknown is alpha, the expansion coefficient. Okay? So we set up our equation. We have delta L over L naught equals alpha delta T. So we're going to have 9.6 times 10 negative 4 divided by 0.5 meters, okay, equals alpha times 80 degrees Celsius. So we need to solve for alpha, so we divide both sides by 80. So as a result, we're going to get 9.6 times 10 to the negative 4 divided by 80 divided by 0.5. You put all that into your calculator, and you're going to get 2.4 times 10 to the negative 5th per degree Celsius is your expansion coefficient for this metal rod. And this here covers expansion, thermal expansion, our last topic for our unit on thermodynamics.